We're going to look at learning objectives B, C, and D in one video. So we're going to start talking about or probabilities where things are mutually exclusive, or probabilities where they're not mutually exclusive, and just counting principles of events that are not mutually exclusive. So really just diving into different forms of probabilities. Now, notation that's important to notice is this one right here. Remember the symbol. This means union. So if we're looking for a word, it means or. Again, right here in this formula, we see A union B, or that means or. So this top formula deals with the counting principle. The bottom one deals with the probability. Look at their writing. They have N. So this means the count of things in set A or B. If someone says, what's the count of things in A or B, you take the count in A plus the count in B. If they're talking probability, that means just a fraction. The notation here is P for probability. So the probability, it's in set A or B, would be the probability of A, and then you add to it the probability of B. Now, these are of events that are considered mutually exclusive. So remember, mutually exclusive means they have nothing in common. So let's first talk about computing probabilities of just a single event. Our event here is that the sum of two dice equals whatever it is. So here we have our 36 outcomes of two different dice being rolled. They want to know of these, what is the probability the sum is a 2? The sum is a 2 happens right here at Snake Eyes. There's only one of them, so it's 1 out of 36. Now the sum is a 3. That's going to happen here at 1 and 2 and 1. So that's 2 out of 36. The sum is 4. 1, 3, 2, 2, 3, 1, 3 out of 36 for this one. Now that the sum is 5, we're going to have a 1 and 4, 2 and 3, 3 and 2, 5 and 1. That's 4 out of 36. Now hopefully you start seeing a few patterns. The patterns in these numbers, it's going to go 1, 2, 3, 4. It's going to get hit a maximum point and then come back down. The one that is the most likely to happen is this diagonal right here. If you look at this and how it's written, it's the sum of 7. The sum of 7 is going to happen up to 6 times, so that's 6 out of 36. Let's put in the sum of 6 as 5 out of 36. And then what's going to start to happen, the sum of 8 is going to back down from 6. It's only going to happen 5 times. It's 1, 2, 3, 4, 5. And notice these sums happen in diagonals, so it's pretty clever that the pattern that you see. So this is 5 out of 36, 4, 3, 2, and 1. So let's use these calculations over here to answer some questions. Let's do one here with the probability. So let's try applying these formulas. What if I ask, what's the probability if the sum is a 5, or I say that the first die shows a 6. Okay. If we do the formula, what we would do is just break it to this. First one would be the probability the sum is a 5. Then I would add to it the probability that the first die is a 6. Okay, the sum is a 5. I can either look at our table here, or if I look at the dice, the sum of 5 is going to be these 4 right here, which makes sense. We said 4 out of 36. Then I'm going to add to it here that the first die is a 6. So if I look at the scenarios where the first die is a 6, it's going to be here. First die is a 6 happens in 6 out of 36 cases. If I add those together, I get 10 out of 36, and then this can simplify to 5 out of 18 as a final answer. Now, I could have asked the question by counts instead. What if I said, tell me for the numbers that how many happen where the sum is equal to 5, or the first die is a 6, so I would add to it the first die is a 6, If you look at that again, how many make the sum of 5? There's 4. First die is a 6. We have 6. So in this case, our answer would be a numerical count of 10 versus the probability of it down here. Now, the last two formulas were for mutually exclusive events. These two formulas just have a slight change. Again, we're dealing with the counts, or the numbers of A or B. What we're going to do is take the counts of one plus the count of the other. But this time what they're going to do is they're going to subtract out anytime A and B have anything in common. So these are for events that are not mutually exclusive, means they have something in common. This Venn diagram drawn over here, we're seeing the not mutually exclusive, or that what they have in common, as the intersection or the overlap. The probability formula is the same way. The probability of A or B, for union, it looks like this. So you might see the math shorthand. It just means the probability of A plus the probability of B minus the probability of A and B. Again, this A and B is really if there's any overlap or intersection. I recommend just always using this formula here and adjusting it for either mutually exclusive or not mutually exclusive. If the events have nothing in common, are mutually exclusive, then this right here becomes 0. If they do have something in common, means they're not mutually exclusive, then this will be a number. So again, I just use this formula all the time and adjust for this component. Now in this problem, we're at a high school. There's a total of 298 students, and they study either only French, only Spanish, or both languages. So they are going to be part of some language. The school says that 115 study French, 209 study Spanish. But if you think about it, if you add 115 and 209 together, that actually exceeds the number 298. So that means there must be students who study both languages. How many are there? Well, a Venn diagram is actually pretty handy for this if you want to see it. I'll put French here, Spanish here. We have 115 French. We have 209 that speak Spanish. Now there's only a total of 298 students, so to find it, what you can do in this case is you can actually say it's going to be the 298 minus the 115 minus the 209, and in this case it means there's 26. So on a Venn diagram, these are the kids that speak both French and Spanish. That notation is and there's going to be 26 of them. So I'd have to be careful now though. Notice my Venn diagram. If I look at the French circle for what I wrote, if I look at it, it looks like there's 115 plus 26 students. That's not the case. So if you do a Venn diagram, you have to adjust it. How many actually speak French in total? We know is 115. So those that just speak French would be 115 minus the 26, and that's going to be 89. So in this Venn diagram, if you look at it this way, the 89 that speak just French, the 26 that speak both, if you add these two up, you'll get the 115 that speak French. Spanish is going to work in the same fashion. So if we adjust that one, this is the circle for Spanish. There's 209 in total. I already have 26 of them. So 209 minus the 26 is going to leave me with 183. So I'm going to adjust my circle and say it's 183. So if I add these two numbers together, I'll get the 209. Now if you add up the 89, the 26, and the 183, you will get the total of 298 students. Now this example is going to ask us about probability again. So I'm going to jot down this right here. Probability, remember, of A or B is the probability of A plus the probability of B. But then we're always going to think about what is the probability of A and B. Sometimes this component is applicable, other times it's not. Here's a scenario. A pair of 6-sided dice are thrown. The dice are fair. What's the probability it shows doubles or a sum less than 10? So what I'm going to write is the probability of doubles, or I'll put sum is less than 10. Now the formula would say it's equal to the probability of doubles plus the probability of the sum is less than 10. But then I'm always going to say, do I have to subtract anything out? And it would be this, the probability of doubles and the sum is less than 10. Let me show you with this dice what I mean. To find the probability of doubles, we have the doubles happening right here. And there are going to be, of the 36, 6 of them count. So I'll say 6 out of 36. Now I'm going to look at the probability the sum is less than 10. Now if the sum is less than 10, that means it could be, 9s, 8s, all the way down to 2. So the sums that are less than 10 are all in this blue region. If I count those up, there's 30 out of 36. Now, this last component, what this means right here, says, wait a second, you have to look, in particular, look at your drawing. Is there anybody that had doubles and the sum was less than 10? Because if you did, what happened is you're going to notice you double counted them. This one, and this one. We have 4 of them that were double counted. So I really just look at this third piece of the formula is getting rid of anything I double counted. So I have to back out 4 out of 36. When you do this, you're going to get that the answer is 32 out of 36. You can actually pull a 4 out of those, so it'll be 8 out of 9, or 8/9 is the answer. So this case, the two events are not mutually exclusive, which means they did have something in common, so the third part of the formula did apply. Okay. Let's look at this one. We have our pair of 6-sided dice again. We're looking for the probability that exactly 1 shows a 3 or the sum of the numbers is greater than 9. So it's the or probability, so I will just do the probability exactly, just write this, 1 shows a 3 in its or, so I'm going to say plus the probability that the sum is greater than 9, but then I'm always going to think about this, do I have to double count anything? So exactly 1 is a 3, and at the same time, did I have the sum was greater than 9? Now if I just do it on the sample space here that I see, it will pop off the page and I'll see if I double counted. So exactly 1 shows a 3. In that case, if I look at those, we are going to have all of those, and we're going to have all of these, except in this one I have to be careful. This guy here is not included. So if you count how many there are, there's going to be 10 that show 1 3 exactly. Okay, now I'm going to add to that those that have the sum greater than 9, and the ones with the sums greater than 9 are going to be these 6 right here, so that is going to be 6 out of 36. And if you look at what I've actually included on the diagram, you don't see anyone overlapping. So is there any case where exactly one of them is a 3 and at the same time the sum is greater than 9? This is impossible. It doesn't happen. It's 0. These events happen to be mutually exclusive, so the third part of the formula didn't apply, but I like to check it. So if we simplify, we get 16 out of 36, and that's going to simplify to the fraction 4/9. Let's try a third one. And again, let's use the whole formula and we'll see if it's mutually exclusive or not. We have the 2 dice tossed. They want the probability that the sum is a 2 or a 3. So sum is a 2 or a 3. So probability sum is a 2 plus the probability that the sum is a 3. But then back out if the sum is a 2 and at the same time the sum is a 3. Okay. The sum is a 2 is right here. There's going to be 1 case out of 36. Sum is a 3. I have 2 out of 36. I can tell there's no overlap, but think about it. The sum is 2, and at the same time, the sum is a 3. You can never get the sum of 2 and the sum of 3 at the exact same time. It's impossible. These events are mutually exclusive. Fraction goes to 3 out of 36, which is going to be 1 out of 12.